Good morning everybody. Today's topic we are going to discuss is properties of liquids. First, let us all know what is a liquid. Liquid is one of the four fundamental states of matter and is the only state with a definite volume but no fixed shape. This is because of the tiny vibrating particles of matter such as atoms and molecules held together by intermolecular bonds which are weaker compared to solids. Also, the intermolecular spacing between the molecules in a liquid is more compared to the solids. Here are the few slides showing the different views of a liquid. Next, we shall define what is the thrust exerted by the liquid. Thrust is defined as the normal force exerted by the liquid on the surface wherever the liquid is in contact. The normal force means the force is acting perpendicularly on the surface, hence it is called the normal force. We can see the figure here, it shows the force acting in both the directions. In two directions we have shown. This happens all along the surface of the beaker wherever the liquid is in contact. Since we have defined thrust as the normal force, thrust will also have the same unit as force. The SI unit of force, as we all know, it is Newton. Thrust also has the same unit, that is Newton. The dimensional formula of thrust is m1 L1 T minus 2. Next, let us define what is the pressure exerted by a liquid. The pressure is defined as the thrust exerted by a liquid per unit area of surface. If a force F is acting or exerted by a liquid normal to the surface area A, then the pressure due to the liquid is equal to F by A. Thus, pressure is equal to thrust by area. The dimensional formula of pressure is thrust. We already saw the dimensional formula is m1 L1 T minus 2. So, that we have substituted there in the formula, and area has the dimensions L2. So, overall, on simplifying, the dimensional formula of pressure reduces to m1 L minus 1 T minus 2. The SI unit of pressure is Pascal. Also, we can write it as Newton per meter square, because thrust is measured in terms of Newton and area is measured in terms of meter square. The CGS unit of pressure is dynes per centimeter square. 1 Pascal is equal to 10 dynes per centimeter square. Next, let us derive an expression to calculate the pressure at a point in a liquid which is at rest. Here we have taken some liquid of density d kg per meter cube in a beaker, and we have immersed a pipe. The height of the pipe we write it as h, or we take the height or length of the pipe as h. The radius of the pipe is r. Now, when the pipe is immersed into the liquid, the pipe also gets filled with water, and the water inside the pipe will exert some thrust on the walls of the pipe. So, we have considered a liquid of density d kg per meter cube in a vessel. We have considered a point P at a depth h inside the liquid. To find the pressure, we are going to find the pressure at the point P due to the liquid. So, we have immersed a cylindrical column, we have immersed a pipe that we consider as the cylindrical column of the liquid, which has a base area A around the point P and height h. The liquid exerts thrust on the base due to its weight. This column of liquid is balanced by the upthrust of the liquid. Thrust due to liquid is equal to weight of the liquid, that is equal to mass of the liquid into acceleration due to gravity, that is mass into g. But density is calculated as mass by volume. So, we can write volume into density as mass. So, volume into density, mass we have replaced it as volume into density, and that into g gives the weight of the liquid column. Also, the volume of the cylinder or the volume of cylindrical column of water is calculated as the base area into height of the cylinder or pipe. So, volume is replaced as A into h, and hence we get A into h into d into g. So, thrust is equal to A h d g, where A is the base area of the pipe, h is the height of the pipe, d is the density of the pipe, and g is the acceleration due to gravity. So, pressure is calculated as thrust by area, and we get it as A g d g, A h d g divided by A, that is equal to h d g. Following are some properties of a liquid at rest. Pressure at a point in a liquid increases with the depth of the point. This can be shown here from this slide. Here we have taken some liquid in a jar and we have made holes at different heights. We can see that the water is coming out of those holes, and the velocity with which the water flows out is more at the bottom and it is the least at the top, because the pressure at the bottom is more and the velocity of water with which the water flows out is more at the bottom, and it goes to a falls at a longer distance away from the jar, that is shown in the figure. Secondly, the pressure at a point in a liquid at rest is the same in all directions. So, if we take a point P, at any point P inside a liquid, it will exert the same amount of pressure in all directions, all 360 degrees, upper and downward pressure will be the same. So, in all 360 degrees direction, the pressure exerted at a point P inside the liquid will be same. Thirdly, the pressure at all points in a liquid in the same horizontal level is the same. This is because the height of a horizontal level will remain same at any point in the same horizontal level. Hence, the pressure P is equal to dgh will remain the same at all points in the same horizontal level. Liquids seek their level, that is the fourth property due to the pressure exerted by the liquid, that can be shown here in this slide. Liquids seek their level. When the tap is closed, we can see the height of the liquid is more in one on one side of the U tube and it is less on the other side of the U tube. Whereas when the tap is open, the pressure is equally distributed, hence the height of the liquid is same in both the tubes. Fifth property, the free surface of a liquid at rest is always horizontal. So, the free surface of a liquid at rest, the topmost surface of the liquid is which is at rest is always horizontal. It never moves in any other direction except horizontal. It is at rest. Sixth, the liquids exert pressure equally in all direction. This is the Pascal's law and all liquids obey this Pascal law. Here are the slides again to show the pressures, examples for pressure. Here the fish tank, we can see since the pressure at the bottom is high, the wall should be thick at the bottom. The pressure is low at the top, so we can have a thin wall at the top. Pressure is exerted equally in all directions. The next topic is the cohesive and adhesive forces. The attraction between the molecules of same substance is called molecular cohesion, and the force of attraction is the cohesive force. For example, the cohesive forces are greater in case of solids, lesser in liquids and least in case of gases. The attraction between the molecules of different substances is called molecular adhesion and the force of attraction is the adhesive force. Example, water sticks to the board, band-aid, etc. are some examples of adhesive forces. Lubricating oil depends on the degrees of cohesion and adhesion. Here this slide shows some examples of cohesive force. We can see the liquid drops are cohered to each other when they are dropping out. Here you can see the examples of cohesive force. This is an example of adhesive force. There is a force of attraction between the water molecules and the stick. The water soap bubble and the wire. Grass and water. This is the lubricating oils which depend on the cohesion and adhesion. Next, shape of liquid meniscus. Molecules of water adhere more strongly to clean glass than they cohere to each other. Due to the sideways adhesive drag, the free surface of water in a glass container is concave. This is the case with all liquids which wet the glass. Hence, the wetting liquids take a concave shape as in the slide here. First is the concave shape of wetting liquids. The second one is the convex shape of the non-wetting liquids. In case of mercury, the molecular cohesion is more than adhesion. Mercury sticks to itself than it does to glass. Due to inward pulls of cohesion, the free surface of mercury in a container is convex, as we have seen in this picture. First one is the concave shape of wetting liquids, and the second one is the convex shape of non-wetting liquids, as in case of mercury. The same thing is depicted when we immerse a capillary tube into water and mercury. We can see the same convex and concave shape. Convex shape for mercury, concave shape for water. Next, let us define the term called angle of contact. The angle between the tangent to the liquid surface and the solid at the region of contact inside liquid is called the angle of contact. The angle of contact is formed due to the differences in force of cohesion and adhesion. Here we can see, when a drop of water is placed on a glass plate, the water spreads, as in your second figure, the water spreads, and at this point of contact, that is when the liquid is in contact with the glass, if we draw a tangent at that point, we can see the angle made by the tangent S with respect to the surface SG is called the angle of contact. Similarly, for mercury, when a drop of mercury is placed on the glass, the mercury takes a perfect spherical shape because the cohesive force is greater than the adhesive force. Hence, if we draw a tangent to this sphere of mercury where the mercury is in contact with the glass, we can see the tangent is making an angle greater than 90 degrees. Whereas that for water, the angle of contact is less than 90 degrees. Normally, the angle of contact for water is taken as 0 degrees, and for all other liquids it lies between that of water and water and mercury. Surface tension. Before going to the actual definition of surface tension, let us know some illustrations for surface tension. If we take a razor blade and place it flat on the water surface, the water curves up all around the edge of the blade and it floats. If it is slightly pushed, the blade will sink, breaking the layer at the surface. Also, if a needle is slightly oiled so that the water cannot wet it and laid carefully on the surface of water so that the film is not broken, it floats. It cannot be observed that the surface is depressed under the needle. This shows that the film is exerting an upward force on the needle. Also, when a shaving brush is dipped in water and taken out, the bristles of the brush come closer. When it is immersed in water, the bristles move apart, and the brush, when it is removed out, the bristles of the brush come closer and stick to each other. This is due to the binding of the bristles together by thin layers of water. Now, let us see the molecular theory of surface tension. If we take a liquid, we know liquid is made up of the small tiny particles called atoms or molecules. If we take water, water is made up of water molecules, H2O molecules, and the blue dots depict the water molecules inside a liquid, inside water. So, if we take a single molecule inside the liquid, it exerts a force in all direction, a force of attraction or cohesive force in all directions. That is, it attracts its neighboring molecules with equal forces in all directions. Whereas, the one we see at the surface, free surface of the liquid, we can see it is having only sideward forces and downward forces of attraction, because there are no molecules above the free surface. The molecules are present only below the free surface. So, every molecule of a liquid will be attracted by other molecules surrounding it. Such a force of attraction exists over a small distance. A molecule of liquid experiences attraction by all other molecules within this small distance, and we call that as the range. If a molecule of a liquid is considered sufficiently well inside the liquid, all surrounding molecules attract this molecule. Owing to symmetry, the resultant force on the molecule shall be 0. Consequently, the molecule is free to move. Suppose a molecule on the surface is considered. Molecules of liquid below this molecule drag it downwards, and there are no liquid molecules above to counterbalance the downward drag. As a result, the molecule on the surface of liquid will be pulled sidewards and downwards. This is with respect to all the molecules on the surface and sideways. Downward drags make the surface of liquid a stretched membrane. This shows that the surface tension exists only on the free surface of liquid. The surface tension is mathematically calculated as the tangential force per unit length across an imaginary line. If F is the force across a line of length L imagined on the free surface of liquid, then surface tension is equal to T is equal to F by L. The dimensional equation T is equal to F by L is calculated as, the dimensional formula for force is m1 L1 T minus 2, and that for length is L1. So, the L and L gets cancelled out. We get the dimensional formula for surface tension as m1 L0 T minus 2. The unit of surface tension is, the SI unit is newtons per meter and the CGS unit is dynes per centimeter. The next we are going to see is capillarity. When a capillary tube is inserted in a liquid, the levels inside the capillary tube, we can see as in the picture, the levels are actually greater than or lower than the actual level of liquid in the beaker. For some liquids where the coercive force is less than the adhesive force, the water or the liquid rises up in the capillary tube, as in case of water, and for some other liquids where the adhesive force is less than the coercive force, as in mercury, the liquid falls below the actual level in the beaker. So, the liquid either rises above the level or falls below the level. Together we call this as capillarity. Next, let us derive an expression for the rise of liquid in a capillary tube. Suppose a capillary tube is dipped into a liquid of density D. The radius of the capillary tube is R and the surface tension of the liquid is T. The density of the liquid is D. Then to what height the liquid rises in the capillary tube can be calculated, and that we call it as the rise of a liquid in a capillary tube. Now, let us consider a capillary tube of radius R dipped in a liquid of density D and surface tension T. Suppose the angle of contact of liquid with glass is theta when the tube is dipped in the liquid. Let h be the height through which the liquid rises in the capillary tube. Though there is downward pull due to gravity for the weight of the liquid column, the column is still balanced. This shows the existence of an upward drag trying to keep the liquid column in equilibrium. The upward drag is due to the surface tension of the liquid. The surface tension T acts tangentially to the liquid surface at the angle of contact theta. If the surface tension T is resolved into the components, one along the y axis and the other one along the x axis, we see the x component or the horizontal component is T sin theta and the vertical component is T cos theta. The upward drag is due to the surface tension and it acts tangentially to the liquid surface at the angle of contact theta. The vertical component is T cos theta, the horizontal component is T sin theta. The T sin theta being equal and opposite to each other cancel out, and only the upward drag due to the vertical component, that is the T cos theta, acts on the liquid, and this vertical drag acts all along the circumference of the capillary tube, and hence the total upward force is equal to 2 pi r into T cos theta. At equilibrium, we know the liquid of liquid column should be equal to the upward force, that is 2 pi r into T cos theta must be equal to the weight of the liquid. Weight of the liquid is m into g, and m can be written as d into v. So, d into v into g, and also we know the volume of the liquid is pi r squared h. So, pi r squared h dg is the total weight of the liquid column, and that must be equal to 2 pi r into cos theta into T. So, simplifying this, we get the height of the liquid in the capillary tube as 2T cos theta by R dg, where T is the surface tension of the liquid, theta is the angle of contact, R is the radius of the capillary tube, D is the density of the liquid, and G is the acceleration due to gravity. For water, as I told earlier, the angle of contact is taken as 0 and the density is 1 gram per cc or 1000 kg per meter cube. Substituting these values, the surface tension of water is given as T is equal to h r g by 2, where h is the height to which the liquid rises in the capillary tube, r is the radius of the capillary tube, g is the acceleration due to gravity, and the height to which the liquid rises can be calculated as 2T by Rg. Next, let us look into the factors affecting the surface tension of water or liquid. Surface tension of a liquid decreases with the increase of temperature. Surface tension of a liquid decreases with the increase of temperature. At a particular temperature called critical temperature, surface tension of liquid becomes 0. This is the graph of surface tension versus temperature. We can see as the temperature increases, the surface tension decreases. Secondly, the surface tension of liquid is directly depending on density of liquid. Here. Thirdly, the surface tension depends on the impurities or surface contaminations which occur in the liquid. The impurities or the surface tension contaminations increases the surface tension. For example, we can see here the contaminated water, the surface tension increases and it may helps the mosquitoes to rear in that water. And also when we use some other impurities like detergents, we can reduce the surface tension. So, the surface tension reduces with certain addition of impurities. Also, the surface tension depends on the some other impurities which will increase the surface tension of the liquid. For example, the gels used in inks increase the surface tension and does not allow the ink to spread over the paper. See, as the concentration increases, the surface tension decreases. Next, let us see some applications of surface tension. The liquid, due to the surface tension, any liquid will be perfectly spherical in the absence of gravity. This effect can be observed or this is used in the manufacture of lead shots. When molten lead is dropped from very huge heights, the lead shards come out with a perfectly spherical shape. When oil has a lesser surface tension than water, hence when a drop of oil is poured on water, it spreads into a very thin layer and it reduces the surface tension of water. This is used by the sailors to calm down the turbulent waters in the sea. When oil is sprayed on turbulent waters, the surface tension reduces and the turbulent waters calm down. In rainy season, oil is sprayed on surface of water in pools and ponds so that the oil film will reduce the surface tension and it will not support the mosquito eggs, as in this figure. This is an example of lead shot. Surface tension is also used in thermometers. When the temperature increases, the surface tension increases and also the liquid mercury rises in the capillary tube in the thermometer. When oil is sprayed on water, the surface tension reduces and we can see the oil has started, it is not floating but it has sunk into the liquid. The next topic we are going to discuss is the viscosity of the liquid. When a fluid is set into motion, we defined the pressure and surface tension when the liquid is at rest. Here we are defining viscosity when the liquid or the fluid is set into motion. Fluid includes both liquids and gases. The different layers of fluid move with different velocities. When a jar containing water is tilted, the top layer of water slides over the lower layers of water. Just as there is friction when one surface of solid slides over another, there is friction when one layer of liquid slides over another. This friction is called viscosity. The property of a liquid by virtue of which it opposes relative motion between its different layers is called viscosity. And if we take the difference in velocity as dV and the separation between the different layers as dx, the velocity gradient is the rate of change of velocity with distance measured normal to the direction of flow. Here are some of the pictures depicting the viscosity of liquid. If the viscosity is more, the liquid flows slowly. If the viscosity is less, the liquid flows faster. Next, let us see the Newton's law of viscosity and how to measure the viscosity of a liquid. Newton showed that the viscous force F acting tangentially on any liquid layer is directly proportional to the area of the layer of the liquid and also directly proportional to the velocity gradient. So, F is directly proportional to area of the layer and also is directly proportional to the negative velocity gradient, minus dV by dx. Combining the both together, we get F is directly proportional to minus A dV by dx, or F is equal to minus eta A dV by dx, where eta is the constant of proportionality called the coefficient of viscosity or viscosity. The coefficient of viscosity of liquid is said to be 1 twice when it requires a tangential force of 1 dyne for each square centimeter of liquid layer to maintain a relative velocity of 1 centimeter per second between two layers separated by a distance of 1 centimeter, or the coefficient of viscosity of liquid is said to be 1 Newton second per meter square when it requires a tangential force of 1 Newton for each square meter of liquid layer to maintain a relative velocity of 1 meter per second between two layers of liquid separated by a distance of 1 meter. The dimensional equation of viscosity, that is coefficient of viscosity eta, we can calculate now according to the formula Newton's law of viscosity. F is equal to minus eta A dV by dx, or the coefficient of viscosity is equal to F into dx by A dV. Here we are neglecting the sign because sign is not going to come to the dimensional equation. Force has the dimensional equation m1 L1 T minus 2. Distance is measured in terms of meters, so the dimensions are L1. Area is meter square, so the dimensions are L2. The velocity has the dimensions L1 T minus 1. Simplifying, we get the dimensions of coefficient of viscosity as m1 L minus 1 T minus 1. The unit of viscosity. If we measure the the quantities in CGS units, that is if a force of 1 dyne is acting on an area liquid layer of area 1 centimeter square separated by a distance 1 centimeter with a velocity gradient 1 centimeter per second, then viscosity is said to be 1 poise. Viscosity is said to be 1 poise, or 1 poise is equal to 1 dyne second per centimeter square. The SI unit of viscosity is Newton second per meter square. If we convert the SI unit to the CGS unit of viscosity, that is Newton second per meter square to poise, we know that 1 Newton is 10 to the power of 5 dynes. Second is as remains as second, but 1 meter is equal to 100 centimeter. So, doing the substitutions, we get 1 Newton second per meter square is equal to 10 poise, or 1 poise is equal to 1 by 10th of a Newton second per meter square. Next, let us see the factors affecting viscosity. The first factor which affects the viscosity is temperature. When the temperature of a liquid increases, the viscosity of the liquid decreases. The figure, the graph shows, if we plot a graph of viscosity versus temperature, as the temperature increases, the viscosity goes on decreasing. Density. As the density increases, the viscosity of the liquid also increases. For example, the density of kerosene is less and the viscosity is also less, whereas the density of castor oil is more, also the viscosity of castor oil or the force which resists the flow of castor oil is also more. Next, applications of viscosity. Viscosity is used in lubricating oils. The ink flows through the pen due to the viscosity of the ink. The flow of ink out of pen depends on the viscosity of ink. The shape of ships, aeroplanes, etc. are streamlined to overcome the viscous resistance of water and air. Viscosity is also used in determining the shape and molecular weight of some molecules like organic molecules, large organic molecules. Viscosity is also used in lubrications. In choosing the proper lubricant, viscosity plays an important role. The viscosity of air and some liquids find application in damping the moving parts of some instruments. Thank you. To conclude, today we have discussed the various properties of liquids like thrust exerted by the liquid, the pressure exerted by the liquid inside a point P, the angle of contact, the capillarity of liquid, the surface tension of liquid and the viscosity of the liquid. Thank you.